Hey everyone, welcome to Astro Seminar. So today it's exciting to have Alisa Galishnikova speak with us. She just recently graduated with her PhD from Princeton University, and now she's at Flatiron as a Flatiron Fellow, and excited to hear about her talk on plasma physics.
Thank you. I'm now joined postdoc fellow between Flatiron and Columbia. Plan to be around a lot, so if you have any questions, please feel free to stop by. And this is mostly the work that I've done during my last years of PhD that I just finished. So I'm mostly interested in plasma pertaining to supermassive black holes. That's what I'm going to talk about. And I'll start with like classical picture that many people in our field start with. The black hole in a nutshell. It's just three parameters, which in astrophysics we have only two, because we never have the charge of the black hole, we have just the mass and the angular momentum speed of the black hole encompassed by the event horizon. But despite their very simple representation in the sense just to make three parameters, they produce very interesting phenomena that we observe in the sky, which are very complicated. This particular example is emission from a giant optical galaxy. So the true color shows optical emission, and radius shown in orange and X-rays in blue. So you can see the powerful jets going shining far beyond the optical galaxy here in the middle.
Why there is this dust? It looks almost like an edge-on spiral, no? Because of this dark light.
Yeah,
what is this?
It's I think it's radio from the obscured radio from the dust. What we think is happening roughly in the systems is that the material from the interstellar medium, stellar wind close to the central black hole is attracted, gravitationally attracted. It's falling onto the black hole, and it brings magnetic fields with the material. These magnetic fields fall onto the spinning black hole, and as the black hole spins, it recycles this material in magnetic field lines and produces powerful jets or blunt prismatic mechanism. That's what we use. So it can produce powerful jets, different outflows, winds, by recycling the interstellar medium. And there is, of course, compelling evidence, as I'm sure you all know, that black holes exist, especially in the center of our own galaxy. And we have this nice Capucine movie of Star Trek orbiting around the central black hole in the center of our own galaxy. Sagittarius A star. And of course, the image by the Event Horizon Telescope is the black hole shadow in the middle. And also, interestingly, these objects not only show quiescent emission, but also show the flaring emission, such as flares produced by Sagittarius A star. And Sagittarius A star in particular shows flares in near-infrared and X-rays. And gravity collaboration observes in the near-infrared circular motion around the central black hole. So there is some kind of flaring emission that is produced very close to the black hole's event horizon.
What do you mean they observe motion? Like like Doppler shifts are consistent with circular motion or something?
It's not like they observe clearly the circular motion, but it's more like astroseismic observation. So you can see the center of emission moving in a circular pattern.
They resolve it?
They don't resolve it completely. So they see the center of emission.
Oh, the centroid is moving
yes,
or something.
Yes, so it's like astroseismic observation, not like they feel
and with the velocity close to the speed of light,
yeah.
I see.
So it's on the event horizon scales, close velocity or orbiting close to current velocity, close to the event horizon. And they observe, there are now two papers with a couple of very clear circular
Because I thought, sorry, can you explain it a little bit, Alisa? I thought the whole claim to fame of this event horizon is because intercontinental interferometry, sub-millimeter, we can resolve this micro-arc seconds. But I thought some infrared telescope cannot resolve micro-arc seconds. How can they see the centroid motion then?
No, they only see the centroid. It's not like.
But what is the resulting like resolution? Is it like also close to tens of micro-arc seconds or something?
It's definitely bigger, but it's also close. It's tens of RG.
Like this kind of size they do see with a single infrared telescope?
I don't quite remember.
Anyway, we can talk afterwards, okay.
But yeah, they now have.
But you are sure it's centroid motion in the infrared?
Yes.
I see, interesting.
Yeah, of course, now we have also another prominent example, Messier 87 and black hole that we observe again with the HT, but also many different wavelengths from radio to X-rays, gamma rays, and we observe the powerful jet extending again far beyond the galaxy, and this is multi-wavelength conveyed by the HT. And yeah, we see the thermal emission, what we think is thermal emission around the black hole close to the one horizon, and also the jet in radio, in X-rays, but also, again, as in the case of Sagittarius, we not only see the quiescent emission from M87, but also we see flares. And for M87, these flares are in a high energy, like TeV range.
So how should the people know about the rotation state of this black hole?
Rotation,
As a
spin.
spin, yeah. Because for the Blanford-Nash mechanism, you need a rotation on the ergosphere.
Yeah. So the jets are very powerful, and I don't think there is any other mechanisms that can produce jets that are this powerful.
But there is no alternative estimation of the spin.
Yeah, estimating spin is very hard because it's not like something that leaves like a clear imprint, because you can, and it's not like you have direct, clear like one-to-one correspondence theory between the spin and the power of the jet.
So you infer it from the jet, basically.
Yeah, so if you feed it from the material onto the black hole, so it's not clear how would you estimate the value of the spin. But in the case of M87, we know very well the inclination of the spin, because we see the jet, and we assume that the jet should shoot along the spin direction of the black hole. And so the inclination of the jet with respect to us observers is around 17 degrees, so it's quite like face-on with respect to observers. So we know well in this particular case the inclination of the spin, but we don't know the value of the spin. And there is the HT library of a bunch of simulations, models that try to match the spin of the black hole with the image, which we think might be, so the spin might correlate with the velocity of the gas. The velocity of the gas gives you the rotation and the Doppler boost. So depending on the velocity, you'll get one part of the image is boosted versus the other. I'll talk actually more about this later. So that's one of the kind of how they try to estimate the spin value, but we don't know the spin values. Yeah, and I want to stress that predominant emission mechanism in the systems is the synchrotron emission. And synchrotron emission originates on small microscopic plasma scales. And from this synchrotron emission mechanism, different observations, we can roughly estimate order of magnitude for the density of plasma, the electron temperature, and magnetic field magnitude. And we know that in this low-luminosity supermassive black holes, the plasma is hot, with the electron temperature being roughly MeV range. Plasma is radiatively inefficient, it's magnetized, with the magnetic field being 10 to 100 Gauss in this parameter ballpark. And also from these parameters, from the temperature and density, we can estimate the mean-free paths of Coulomb collisions. And if we estimate the mean-free paths of Coulomb collisions, we find that it is much larger than characteristic sizes in the system. And in particular, the mean-free path is 1,000,000 times larger than the size of the black hole's event horizon. Varies a little bit from black hole to black hole, but roughly it's 1,000,000 times larger. So the plasma is in fact magnetized and collisionless. And the kind of paradigm over the last years has been to study the non-linear evolution of these systems, linear accretion of plasma into supermassive black holes, the jets, the outflows, using general relativistic linear hydrodynamic simulations. And here I show one of these simulations and one of models that I'm sure many of you heard about, the magnetic arrested disk model, where the accretion is something like that. So the accretion is decoupled into three main parts: the main disk body, the corona with the hot plasma, and the jet region, the recycled magnetic fields.
So on the right, Z is vertical and on the left horizontal.
Z what?
Z is along this spin, let's say, of the black hole.
Yeah.
Here Z is vertical, on the left it is horizontal.
Why?
I don't know why.
Yeah.
What do you mean?
Here Z is horizontal, here it is vertical. Isn't it a jet emanating from the black dot?
What are the colors?
I see what you mean. No, color is plasma beta, so it's high plasma beta here and low plasma beta here. You can see the jet clear in this like, color range. So it's low beta. There is no jet that you can see here. It's the disk, the high beta disk.
Oh, this is a disk, so
Yeah.
it's actually going in, not out, because it gives an impression that it goes out.
Yeah, so this is great observation because in magnetic arrested disk simulations, right, we have magnetized plasma here, it's, beta of...
Oh, it does go out.
Yeah,
That's the nature of, this is
Yes.
frontal jets. Yes, of course, good.
There is the magnetic reconnection, the saturation of magnetic flux at the horizon, and then there is the flux eruption from the black hole. So there are episodes of periodic accretion, but also the eruption. But in general, like it's a 3D accretion. So you have maybe in some 3D space you'll have accretion, in some space you can have eruption.
And in this case, you don't get any jet at all.
You do.
You do? It's
Yeah.
just not seen here.
Yeah, it's just not seen with this color bar. It's from
Or because
from this
some
one.
remnant of BZ is still operating or something.
Or it's just because it's different
Well,
velocity.
you can see
It's
it.
just low beta.
You can see it for a second.
You can't really see another. You can't really see.
Oh, yeah, sometimes, yes, Clinton is right. Sometimes there is this
No,
thing.
it's numerical. Because in MHZ, again, the equation, MHZ approach doesn't like when you don't have plasma vacuum. You have to have some kind of fluid, and jet, in terms of MHZ, like compared to the disk, it's almost empty. So it's many orders of magnitude smaller density. So people have to set like floor values, so they call it stable. So that's another shortcoming.
So this light blue is an artifact.
Yes,
How interesting.
it's an artifact actually of the polar grid.
What are like the conditions? Like there's a constant accretion rate at the boundaries of this thing. Like what's maintaining?
Yeah, so the magnetic arrested disk simulations usually initialized with something that's called, I will mispronounce it, Fishborn monocular torus, which is hydrostatic equilibrium. So it's a rotating, large-scale rotating torus. So in hydrodynamics, it is stable, but when you add magnetic fields, groups of magnetic fields, it goes unstable to something what's called magnetic rotational instability. And you can start actually accreting this tori, which is stable in hydro. And you have like, the boundaries actually, this is a small part of the domain in this simulation. The boundaries are actually very, very far from the black hole. Like, this is 10 Rg, but the boundary, I believe, is something like 10,000 Rg. You have some outflow boundary conditions, so they don't affect what's happening at the horizon. And of course, the another boundary conditions are at the black hole. And there you don't really need any boundary condition because as soon as plasma goes inside the horizon, it is disconnected.
What is beta? Maybe you said it, but what is beta?
Yeah, beta is, sorry, I'll have it on the slides after that. Beta is a ratio between the thermal pressure of the gas and magnetic pressure. So high beta means lower magnetization, and lower beta means higher magnetization. So as the plasma accretes from like high-ish beta, less magnetized, the material will be recycled, and the jet has very high magnetization. That's why it's not visible in this color bar. Okay. Yeah, we spent a lot of time on the simulation that is not mine and that I don't think is very applicable to realistic systems. So let's talk about why it's not very applicable. Yeah, so first, as I said, the mean-free path is much larger than characteristic sizes in the system, and these simulations, the MHD simulations, assume that the plasma is fluid, it's thermal, and so any anisotropies will be instantly isotropized by collisions in the plasma. That's what is meant by fluid or particles that are common to us. This is when the mean-free path is much smaller than characteristic sizes in the system. You'll have isotropic temperature in 3 dimensions. It's all isotropic, all directions. But when you have collisionless plasma, it doesn't have to instantly isotropize any anisotropies, and moreover, when you have magnetized collisionless plasma, you'll have special direction. So imagine you have 3 dimensions and also the magnetic field. So now temperature of plasma doesn't have to be scalar, it's a tensor quantity. And we can represent it, for example, as temperature perpendicular and parallel to the magnetic field direction. This is for magnetized and collisionless plasma. And this is not used in the solar physics community, where in this work you can see distribution of ions in the solar wind. And here they show the ratio of perpendicular and parallel temperatures of ions in the solar wind. And this is plasma beta, parallel plasma beta. So yeah, here I know that plasma beta is thermal pressure over the magnetic pressure. And what is important in this plot is that the isotropic plasma would be just this ratio being 1. But you can see there is a whole distribution with this ratio being smaller or larger than 1. So plasma in solar wind is actually anisotropic. And what's happening, for example, what might be happening is that in the solar wind, or in any plasma, you will have to preserve adiabatic invariants, which I note here, which involve pressure or temperature perpendicular and parallel to the magnetic field direction, magnetic field magnitude, and plasma number density. So imagine you have a patch of plasma, and you start to increase your magnetic field, so then the perpendicular pressure has to increase here, and parallel temperature has to decrease. So you'll be left with this kind of anisotropy, with perpendicular temperature larger than the parallel one. And this is a non-equilibrium state in the plasma, and the plasma actually doesn't like this state and will not be able to go to temperature ratio of infinity or 0, because eventually microscopic instabilities will kick in and they'll limit the amount of anisotropy in the plasma. And so these are what these lines. So this is called Fahrenheit instability, this is called Muir instability, and this is magnetic field fluctuations in local kinetic simulations. So this is just visual representation of how these microscopic instabilities can look like. So you can't grow these anisotropies without bounds, and we can actually observe this in the solar wind that they obey this instability thresholds. Yeah, another kind of anisotropy, but also general heat fluxes. In the ideal MHD approach, all the heat fluxes are 0, but in collisionless plasma you can have heat fluxes, and this heat flux is also anisotropic, heat flux parallel and perpendicular to the magnetic field direction. And finally, another difference I want to stress is the reconnection physics. So imagine you have, these are magnetic field lines, you have magnetic field lines going this way here and this way here, and you have inflow from top and bottom. So magnetic field has to go through 0 here, and how it does that, it goes through the reconnection process. So this is something that's called X point. So magnetic field will have to, on the top and bottom, has to reconnect and turn into this X point. And this is important because this is the same simulation I showed before. In this large-scale magnetic fluorescent disk simulations, we see that the disk accretes through these current sheets, and you can see zoom in here, and there is this X point, and as the magnetic flux here in this current sheet saturates, the magnetic field reconnects, and then you have this flux eruption episode, so that the direction opposite of the accretion that we talked about earlier. So you'll have flux eruption episodes, and the time for the magnetic flux to leave the event horizon will be controlled by the reconnection rate, the rate of the reconnected magnetic field lines. And it is important to consider the kinetic reconnection versus the fluid reconnection, because first, the kinetic reconnection is 10 times larger, the rate of it is 10 times larger than in the fluid approach. It's 0.1 C versus 0.01 in ideal MHD. And also, when we're talking about ideal MHD approach, the reconnection actually happens on the grid scale due to numerical resistivity. But in kinetic plasma, it happens on kinetic scales. So collisionless plasma can naturally capture the scale of the reconnection. And
sorry, what is it? What is a kinetic scale?
so scales of, imagine like plasma skin depth, Larmor radii, also actual scales, kinetic scale, microscopic scales of the plasma.
Okay.
And in the ideal MHD, when you have current sheet, it reconnects on the grid scale of one cell because of the numerical resistivity. That's when it can reconnect. So these are just the differences of the actual connection physics. But also, when you have collisionless plasma, kinetic plasma, you have particles, and when the plasma is sufficiently magnetized, which the sigma parameter is of order of 1 or larger, which is true for magnetic fluorescent disk simulations models, these reconnection sites can actually lead to non-cerebral particles. They accelerate particles. And this reconnection process is believed to be connected to the flares, which is flares of Sagittarius A star. So it happens close to the black hole, leads to non-thermal particle acceleration. So yes, the understanding the behavior of collisionless plasma is the key component to understand, for example, variability of the sources, as the reconnection controls the time to escape for the magnetic flux to escape the event horizon, and also it helps to accelerate particles.
And what is a magnetically arrested disk?
Yeah, so this is just generally what people call this type of models, which have magnetized disk, a lot of magnetic flux, and as a result, they can produce powerful jets.
Okay.
So kind of generally, people think in terms of black hole accretion models falling into two categories: the mad magnetic arrested disk and standard and normal evolution, which is same.
Right.
So that's what these words are. And in same, the magnetic flux, there is less magnetic field and it can't produce the powerful jets. So we think that we need a lot of magnetic flux to produce the powerful jets that we observe. But generally, magnetic arrested disk is just any sort of model with sufficiently large magnetization, sufficiently low plasma beta.
And incidentally, that gravity result you were showing, that's the infrared data you're talking about?
Yes.
Yeah. So that's on VLT. It's interferometry between two separated
Oh,
telescopes.
so it is
Yeah.
interferometry.
It is in the near infrared though.
Ah, I see.
Yeah.
So they have two telescopes at
Two
some
telescopes.
distance?
Yep. They can do amazing things. They can look at the surface of Betelgeuse.
Like resolve.
Result. Yeah.
I see.
Anyway, but that's not that's not what we're here to discuss.
Yeah, okay, so now we have this wide range of scales. So we have the microscopic plasma scales of larger radio with particles where emission actually originates, and we also have the scales of like HT, gravity observations from the event horizon to like hundreds of RG, and also the scales beyond the point radius where we observe the powerful outflows, jets, like this feedback from the black hole into the surrounding medium. And to study this black hole phenomenon, we need to understand the microscopic plasma scale, because this is where the emission originates. So I talked about the magnetohydrodynamic approach, GR MHD approach, but we actually want to use something that is called kinetic approach, or particle and cell approach, which is the first principle approach to simulate plasmas. And you can imagine it being like your generic cube shelf, but it's obviously not 3 by 3. The grid is much larger usually, and you have a bunch of particles inside the domain, moving like inside these shelves. And on the faces and edges of the shells, you have electromagnetic fields. So the simulation loop looks something like that. You have electromagnetic fields on the faces and edges of the shelf. You evolve these electromagnetic fields according to Maxwell's equations. Then the particles inside the shells, they experience a Lorentz force due to these fields. And then they move according to the equations of motion. As they move, particles deposit current, and this current goes back onto the grid. And then this current from the grid goes into the Maxwell's equations, and this loop repeats. So this is the basic loop of the particle and cell simulation.
Do you write these codes or you use them?
Kind of was. Yeah, so for the work I'm going to show, I used code that was already developed. We now developed new kind of architecture agnostic particle and cell code, so which is based on Cocos framework, which you can run on both CPUs and GPUs, which will include both the SR model, so just special relativistic particle and cell simulations, but also the GR model, and it's publicly available, so anyone can use it.
That was my naive question. So you are going close to the horizon. So to what order you have to modify Maxwell equations, taking into account general relativity maybe?
Yes, exactly. So now we need not only to solve for the kinetic.
You broke your IKEA shells.
So you not only need to look at the kinetic physics of plasma, but also you need to account for the presence of strong gravity. So Maxwell's equations, we can just solve the equation of special relativity. We need to account for GR. And what we do in these simulations, we use the so-called 3+1 formalism, where the spatial metric is completely decoupled from the full metric. We simulate it in the Kersheld metric. So in this formalism, you can actually decouple Maxwell's equations from the spatial part of the Maxwell's equations. So you can solve this Maxwell's equations. Then again, particles will feel the Lorentz force computed here, but also they will feel the curvature of the grid. Feel the
Your
gradation.
alphas and betas there that relates H and B are X-dependent.
Yeah, yes, alpha and beta, they are shift and lapse vector. So anyway, shift of the time of the observer, and beta is the lapse vector, basically inertial coordinates. You are always following to the center of the black hole. So that's what this is. So they, alpha and beta, account for the decoupling of the full metric.
Is this approach completing the galactic collisions between the particles?
Yeah, no collisions.
No collisions. It's all on scales much smaller than the mean-free path.
Oh, mean-free path of the systems is larger than the Bondi radius.
Okay.
We don't care about collisions at all. There are, like for example, in lab, plasma, or in other environments, like here collisions should be relevant, but there are particle cell codes that are trying to simulate collisions and different models for collisions, so they need to account for like binary interactions of the particles. So this can be done, but this should not be included in the systems. So there are no collisions, but plasma, has collective effects. So they are kind of, in some sense, they have some viscosity. For example, this stays here. Yeah. So the principle is the same, but the equations are much more computationally expensive, and they account for the actual strong gravity in the presence of the black hole. So the first thing we did was this approach to kind of understand the difference between the fluid approach and kinetic approach. We tried to compare it like apples to apples and try to take the simplest accretion problem, which is just 1D spherical accretion, but with magnetic fields on top of it. And here I show plasma density on the left in the fluid approach and the kinetic approach on the right, and the white lines are the magnetic field lines. And so this is the same problem in axisymmetry, the simplest one, and you can see that the plasma first accretes, then there are these current sheets forming. At some point, these current sheets reconnect here and here, and the flow evacuates.
But it is probably in some funny regime, right, which has nothing to do with the real accretion.
Yes.
So, but the point being that even in a funny regime, there is already a discrepancy.
Exactly.
Okay.
Yeah. So I mean, I wouldn't want to go, just take this huge hammer, and go into a realistic problem. First, one understands apples to apples. What are the differences between MHD approach and the collisionless approach? So you can see that generally the dynamics is quite similar. So most approaches successfully produce the gas dynamics, but of course the fluid approach lacks the non-ideal effects that are naturally present in collisionless plasma. But of course, kinetic simulations are way more expensive. So like MHD always has this advantage of being able to go to way larger scales. And one point that I stressed is the reconnection physics being important, and that it regulates the time for the magnetic flux to evacuate from the black hole's event horizon. And so we can measure the magnetic flux at the horizon as a function of time. And here I show the kinetic approach with this light line and the fluid approach here. And they are quite similar, but also different in some details. So first, the kinetic approach has higher reconnection rate, and the exponential fall down of the magnetic flux at the horizon happens faster this time here compared to here, but also due to the difference in the scale of the reconnection and the way the flux accumulates onto the black hole, we can have some differences in the frequency of disruption episodes. So of course, this is a very toy problem.
How I understand this peak?
Yeah, this is
This, I mean the spurious one.
which one?
I say spurious, the one in which they don't agree.
Sorry.
I mean this peak, the
This
second
one.
one, yeah.
Yeah, so the black hole accretes, then the flow evacuates, it accretes again, and again evacuates. So there are two peaks in the fluid approach, but only one in the particle cell approach. So that tells you that there might be difference in the variability of the systems and the way the flux evaporates from the black hole. And this likely has to do with the scale of the reconnection, because this is only grid scale reconnection.
But to order of magnitude, it's okay, yeah?
Hmm?
To order of magnitude, they agree.
Yes.
So
Dynamics.
it's not that bad.
Yeah. Order of magnitude dynamics is similar. So again, you have kind of effective collisions because of the collective plasma effects. But when you look at the details, these collisions are can be anisotropic, there can be different rates. And there is actually a problem with our USD simulations, how we try to explain variability in the systems and the timescales do not match in real systems and null simulations. So this is like one way to say that if you think about collisionless physics, the timescales will be different. Yeah, and of course, this reconnection sites also lead to non-thermal particles. And for example, you can see this loop here, which reconnects, and by the way, kind of like a flaring bubble, it is filled with accelerated particles, and here we'll have some accelerated particles, which are just naturally present in collisionless approach.
I mean, the fluid approach just can't produce any particles that are non-Gaussian, right?
So there are just no particles,
They're
they
just
are all
not.
thermal.
Yeah.
Yeah.
But do you actually need accelerated electrons to account for the observed radiation? Like those event horizon MHD people who claim to reproduce observations, do they include accelerated electrons?
No, I think they. Well,
Because
most of
maybe
them-
your accelerated electrons don't matter too much.
No, I don't think they matter for HC images because this is probably just predominantly thermal emission from
Right,
the disk.
because they are the bulk of the distribution
Yes,
function
yes.
is actually responsible
But
for.
for the flares, you wanna.
So for flares, it is like for X-ray
Yeah,
flares.
yeah.
I see. So, so these GR people without some ad hoc model would be impossible for them to
Yes,
simulate
yes.
X-ray.
Yeah,
And you, in principle, perhaps, in your dreams, can do it.
yeah, something like that, yeah.
Right.
Yeah, and I mean, we can actually like measure particle spectra. I don't show it here, but I can talk about this a little more. I have a backup slide on particle spectra. Okay, and another difference I talked about is the plasma anisotropy. So this is again where there are no anisotropies in the MHD approach. So this is one of the snapshots from one of the kinetic simulations, and here on the left I show temperature anisotropy. So you can see the parallel temperature is smaller than perpendicular one, and this is just because again the plasma accretes onto the black hole, brings a magnetic flux towards the horizon. Magnetic field increases, perpendicular temperature increases, and parallel temperature decreases. So you have this kind of anisotropy here. And again, this anisotropy kind of grows out bounds. Eventually, kinetic scale instabilities will set in, and this is what you see here. This anisotropy is controlled by the kinetic scale instabilities. So these are magnetic fluctuations, and I show small zoom in here. And the black lines are the magnetic field lines, so you can see this kind of bottle-like structures, and this is actually kinetic scale mirror instability. Yes. So this puts us somewhere here on this plot from the event horizon scales to hundreds of RG, where we find that the general dynamics is similar between the MHD approach and the kinetic approach, but of course there are some important differences, such as the difference in the time scales due to the reconnection physics, or dynamical time scales. Also, have particle acceleration, which we can look at in kinetic simulations, and also find anisotropies. And I don't have time to talk about heat fluxes, but also can measure heat fluxes.
So why does it work? What's your explanation? You have mean free path, which is 1,000,000,000 times greater than your characteristic length scale. Naively, you would think fluid should totally fail.
Yeah.
So what's your explanation for why it still makes sense?
Yeah, I think it makes sense because the plasma is magnetized and there are collective effects in the plasma, which again, like if you look at this bubble, like these particles are not leaving this bubble. Right? They like in principle, if you calculate like not the column collision mean free paths, right, but just mean free paths, they will not escape this bubble because they are magnetically confined there. So in some sense, plasma has like effective collisions. Or these anisotropies, they just provide, people measure actually in these instabilities effective viscosity of the plasma. So it's not actual Coulomb collisions, but it's some kind of effective viscosity, for example. But this viscosity, again, it is not isotropic, as would be in non-ideal MHD approach. Usually we put viscosity in the equations, which is isotropic, but here there will be anisotropic effects. interconnection physics actually is also controlled by anisotropic pressure. So yeah, order of magnitude is very similar, but many important differences in time scales, anisotropies, heat fluxes, particle acceleration, important for understanding flares, which we observe in systems. And in terms of the microscales, we see that there are microscopic anisotropies and also instabilities. So the plasma departs from its thermal equilibrium, and this is actually important because it not only changes the thermodynamics of the system, right? So kind of time scales are changing the dynamics of the system, anisotropies change temperature, thermodynamics of the system, but they also directly change the distribution function of synchrotron-emitting electrons. So if we want to understand the emission from the systems, we need to understand the synchrotron radiation, and usually we think about synchrotron radiation produced by some kind of thermal particles or power law distribution of particles, but here we have anisotropic distribution. And in the disk, we have some kind of anisotropies in the thermal distribution of particles. So this is anisotropic relativistic Maxwellian distribution that we looked at. So this is the usual thermal relativistic distribution, but now you have perpendicular momentum and parallel momentum decoupled from each other and parameterized by this eta parameter here, which is roughly the ratio of perpendicular and parallel temperatures. Right. And then you can do all the usual synchrotron emission analysis. Actually, analytically, it's working totally fine. So you sum up over all electrons over this distribution function. And what you find is that, imagine you have plasma with some temperature, but now you kind of decouple this temperature into perpendicular and parallel temperatures, and you can decouple this total temperature differently into perpendicular and parallel temperatures, which is defined by these eta parameters. So it effectively changes the number of particles that are emitting towards the observer by decoupling this temperature to two different ones. And so the usual synchrotron emission that I showed here, the intensity of emission versus the observing angle relative to the magnetic field. So the black line is the usual synchrotron emission formula here. And if you look at the case that I showed on the previous slide, actually, it's like here, when the perpendicular temperature was larger than the parallel one, you can see that the synchrotron emission is even more concentrated towards larger angles, right? Predominantly emits perpendicular to the magnetic field. But when you have the opposite case, when the parallel temperature is larger, your emission can peak basically at any angle relative to the magnetic field, which is very interesting and very different from the usual synchrotron emission that we think about. And also, that's something that interests you, I can talk about intrinsically emitted polarization fractions, which also changes with these anisotropies. So these are thermal anisotropies, thermal distribution function of electrons in the disk. So it's natural to wonder how it changes emission from the disk, so HC images. And here, as we talk actually about the spin of the black hole, right? We have like spin axis, we have the magnetic fields in the disk like that, and the velocity field lines also like that. The disk is rotating. If you look right along the spin axis, we will see a very symmetric image, just the donut. But when we try to look a little bit off axis, you will see that one part of the image is brighter than the other one. And this is mainly because of the Doppler effect, because this plasma goes away from us, so it's dimmer, and this one goes towards us, so it's brighter. And also, synchrotron emission is predominantly perpendicular to the magnetic field direction, so it matters what is the magnetic field direction in the image plane, and also magnetic field lines are bended due to gravitational lensing. So this is how in the HC images we're trying to understand what is the spin of the black hole and the inclination of the disk of the black hole relative to us observers. And if you look at both of these HT images, as I already said, in the case of M87, we actually know the inclination of the spin. We know the inclination of the spin is just 70 degrees, so it's very kind of face-on. But nevertheless, we observe a significant asymmetry in the image. So one part of the image is brighter than the other one.
So, correct me if I'm wrong, but isn't the people of the Horizon Telescope is also claiming that Sagittarius A star is orbiting like almost perpendicular?
Yes, so exactly. Like this one is almost, so yeah, I want to stress that this one, we know that it's almost face-on and there is significant asymmetry. This one, we don't know the spin because there's no jet, don't know the direction of the spin, and it looks very symmetric. So from the HT standpoint, the image is very symmetric, and that means that we are looking very much face-on. And this seems very kind of fine-tuned, right? So
It could be also that it has no substantial spin. And probably it's not rotating too much.
yeah, so the other answer is that it might have something to do with the low speed, but also then where is the jet, because we see strong magnetic fields. When there are some strong magnetic fields, the spin must be like 0 to make no jet in magnetic arrested disk model. So I think that's
Well, but if it is not rotating, even if there is magnetic field coming from accretion disk or whatever, you will not create the black Force-Nash mechanism because you need rotation as well.
you need spin of 0 to not create a jet, like exactly 0, which also seems very fine-tuned. Black hole in the center of galaxy has been sitting there for years with a spin of
It cannot be
exactly
like a shy
0.
shape that we don't see like.
No, we don't. Well, there are like radio, like this SD, the spectra showing slope, which I think is consistent at like high wavelength with jet models, but it's uncertain, and I'll talk more about this later.
Okay, but that's interesting. So all the claims that I have heard from my friends that say that this guy is rotating like that, it's just they infer that just because of the symmetry of the shadow and the absence of shape. Period.
Yes, that because they
from
don't
where they
don't see a lot of asymmetry, and that's why they assume that
I see. I
it's
thought
pointing
it was
towards us.
some additional evidence.
No, not really. Also gravity. So in terms of the gravity flares, they showed they see the circular pattern and they think that it might be likely that we're drawing the spin that is towards us. It's actually interesting because there are polarization constraints, which is also polarization can give us hint on the spin if we know the magnetic field ordering in the disk. So there are some models that if you don't include like external screen, Faraday radiation screen into the Sagittarius, gravity and HT show that the spin pointing in different direction.
Okay.
And that's also a fun thing. So yeah, asymmetry is important to understand the inclination. And as you can imagine, if we have an isotropic plasma that emits not only just perpendicular to the magnetic field lines, but also any direction, the constraint on the asymmetry on the spin direction will change. So here I show again a toy model of the same magnetic arrested disk accretion problem. But
Does it mean 100 greater than 1?
So that means actually, I showed the instabilities on previous slides, like the solar wind bounded by the mirror and Firehouse instabilities. So here I show the bounds imposed by these instabilities. So these are actually maximum.
And those are
amounts of
beta
absorption.
dependent or
Yes, these are
something?
beta dependent.
But if you assume some beta, like whatever, let's say 10 to minus 2, 10 to minus 1, what are you using for this number here?
So this is actual, I have a backup slide that I can show.
But roughly, I mean, is it a realistically large anisotropy that you are using here?
Yeah, it's like in the solar wind we have
Oh,
near
it's similar to this thing, okay.
fire hose, and then in the solar wind we think that like you saw that the distribution sits like here. So if beta is smaller than like 10 to the -2, which is like very much in the jet region, I just posit 2 constant.
And this constant is over the 10.
Yeah, it's like 10 here and 2.1 here.
Okay,
But
alright.
these are actual. I also considered Whistler instability, but it sits below the mirror. So here I show just mirror instability and fire hose
Okay.
instability. But yeah, it's beta dependent. Yeah, so this is kind of maximum allowed anisotropy. And you can see that the same accretion model has very different images. And not only this has, this is more like asymmetric than this one, but also the direction of asymmetry changes when you consider different anisotropy. Because here plasma emits predominantly actually along magnetic field lines. So not a lot of emission.
And of course, EHT people, when they claim a certain spin, they do not include this thing
No,
at
it's
all.
only thermal function.
Okay. This is nice.
Yeah, so it's interesting that it changes the constraint on the observing angle because of the asymmetry of the image, but also it changes constraint on the black hole mass and gravity constraint, and this has to do with the size of the image. So the size of the image is directly related to the mass of the black hole and the gravity constraint, to the size of the black hole shadow. I can also talk more about this if you're interested.
Does this change over time?
So this is magnetic arrested disk model, which is used here in the EHC simulations. It's actually very stable in the like accretion periods. So this is like averaged over this model for many times.
But EHT averages over long times, otherwise they
Yes.
don't have enough flux, right? So it has to be averaged.
Yeah, although I mean they do have a time evolution. They can average months, and they've observed it for
No,
years.
but because this thing probably changes within one period of rotation, right? As your turbulence, right? Each time it goes around.
Yeah, it's like it fluctuates during one accretion period, but generally the dynamical state is kind of stable.
But you're saying this varies around this
Very
quite a-
quickly, right?
quite a bit, but over time
Exactly.
scales that
Yeah,
are
just
like.
due to like turbulence in the disk, it will vary.
But it's
on
like the
short-term
dynamical
scale, but-
time in the inner parts of the accretion disk.
Yeah.
Okay, so fast.
So one at least good thing that we found in this work is that we assume that in the future next generation HT will be able to decouple the direct emission from the Flatiron emission. They will pick up the anisotropy different, and so we might be able to pose limits on the amount of anisotropy in the accretion flow. Can I go on? So we have, like,
Yeah,
minutes.
yeah, maybe 8 minutes or so, 10 minutes, yeah.
Okay, so this puts us somewhere here on this plot. So if we understand the collisionless accretion and anisotropies in the flow of the accretion black hole onto black holes, understand the emission on small scales, this can allow for a direct comparison of these models and observations. And in the last 5 minutes, I want to go to the other part of the plot and talk about the large scales of this problem. So I've been talking a lot about the magnetic arrested disk model. I'm simulating it at small scales. I'm using it for post-processing, for understanding if the collisionless physics is important, but is this actually a generic state of the accretion? So in the magnetic arrested disk, same picture that I showed before, main disk body, corona, jet, we have very magnetized inflow. The magnetic flux piles up at the horizon. There's some connection, that flux eruption episodes, subsequent flares. Also, the magnetic field is recycled into the jet by a blunt-snag mechanism. But the material accretes from the interstellar medium and stellar winds, and also this simulation start usually with magnetized torus, which is not necessarily realistic initial condition. We somehow have torus around the black hole. And of course, another elephant in the room is that Sagittarius A star shows presence of strong magnetic fields, but also doesn't show the jet. So it's interesting to understand if the magnetic relativistic disk scenario is actually a generic outcome of magnetized accretion. So to study this, I looked at the kind of simplest magnetic flux accumulation model that you can think of, similar to what I showed before in the collisionless accretion problem. So the simplest flux accumulation model is just spherical pointy accretion, but you put a colloidal magnetic field on top of it to accumulate as much the magnetic flux as possible. So instead of starting with a magnetized torus solution, we start with just spherical accretion with magnetic flux on top of it. And this is not something new that we studied. It's been studied actually recently with numerical simulations in different works, but we found that the results seem to be like incompatible with each other and in different parameter regimes. So we tried to unite these results in this study. So this pointy spherical accretion with magnetic field has just a couple of free parameters. It has the black hole spin, the pointy radius of this random medium, so pressure, temperature, and also magnetic field strength, plasma beta, and maybe its orientation, and initial angular momentum. So to get to the maximum jet power, you would imagine your spin to be high, and you can imagine as much magnetic flux as possible, so just a lot of colloidal magnetic flux, vertical magnetic flux along with the spin direction, so that the high spin can recycle these magnetic fields into the jets. So this would be the simplest scenario, right, to recycle magnetic fields in the spherical accretion to get to the jet. Okay. And so you're left with this pointy radius and initial angular momentum parameters and the plasma beta. But let's say the plasma is initially magnetized, so beta is much larger than 1. So this is what we found for the parameter regime that is similar, that studied in the literature. In color I show here, this is GRMHD, so the simplest model to accumulate magnetic flux. This 3D simulation of the setup, in color I show plasma beta, and the magnetic field lines are the white lines that originate around the black hole here. And so this is very similar to what was found before for this kind of scenario, but also for the magnetic relativistic disk scenario. Magnetic flux accumulates in the black holes, we have magnetized inflow. As a result, you have magnetized powerful jets here. This would be big phi magnetic flux, magnetic field lines.
I want to be sure I understand the geometry. So it looks like there's almost a monopolar-like thing, and then the gauzy thing inside is the highly twisted magnetic field?
Yeah, here, like magnetic field lines here are vertical.
Right.
Yeah, so they
I was
accrete.
thinking about more in the center, right?
So they accrete, they'll stretch, BR, radial field will stretch.
So they're basically continue to be vertical but pinched, and then there's the twisted part.
Yes,
Is that the way
yeah.
you see it?
So as you'll accrete the colloidal magnetic field, you will preserve your B theta, right? You will just adduct your B theta, but the radial field will be stretched, so you'll have like a pinched magnetic field here. You'll have like current sheets here. So here you'll have current sheets, they will reconnect, there will be flux eruption similar to that, and the accreted magnetic field will be recycled. The Blenford's-Neck process into this jets.
What I want to be sure I'm understanding is because the visualizations people have always used in the past are these sort of cone-like things with a spiral field around it, as if the spiraling field is holding in this containing the pressure of the cone or something. But here, that's not what I'm seeing. It's not spiraling, it's dipping in, and then there's this gauzy thing in the center that's more like a amoeba or something.
You mean these field lines?
It's a cocoon.
Yeah.
Or these ones? You mean these
They
field
seem
lines?
sort of distinct, I guess, is what I'm struck by.
Because the field lines here will be connected to like the disk region.
Yeah,
and
yeah.
here they will be connected to, this will be causally connected to the jet.
It's just somehow much more, what would be a physical time scale if you were to scale this thing up to a M87? What would be the wiggling time?
Oh, wiggling time of the jet.
Yeah, yeah.
So this is different from math simulations in terms of it is spherical accretion, and the jet has to go through some material to propagate. And so there will be current in the jet and material pressure around it. And so this current and the jet is actually kink unstable. So this is current-driven kink instability. So in math simulations, this is stable because you don't have any medium for the jet to propagate through. But here it's spherical accretion, it's trying to propagate through this medium, and it is unstable on large scales, on scales like of Bondi radius and beyond Bondi radius, it is unstable. So it's not constantly straight jet on scales.
This looks anything but spherical, so what does it mean exactly as spherical accretion?
Like if you exclude the magnetic field from this picture, you'll end up with just one dissolution. But you take one dissolution and put colloidal magnetic field on top of it.
So the initial conditions are spherical, but then of
Yes,
course,
yeah,
and then there's a spin, presumably also.
yeah. Yeah, right, so if you have a non-spinning black hole without magnetic fields, it will be one dissolution. And if you have spinning black hole without magnetic fields, it will also be one dissolution.
For the galactic GR effect, it would be spherical still, because it looks spherical.
Well, right. Yeah, but interesting things happen when you actually go to you're trying to go to a more realistic case. So, as you remember, we have just two free parameters. Basically the Bondi radius and the initial angular momentum. So I keep initial angular momentum here to 0, it's non-relevant as of now. You can see that now you have jet, now you don't have a jet. So it is not very similar if you increase Bondi radius. You still have a lot of same magnetic flux in the surrounding medium, it accretes, but then you don't recycle somehow it into powerful jets, and of course the jets are unstable on large scales as well. And so you end up with these two, kind of in this parameter regime, with two distinct states. When you have, for a smaller Bondi radius, you have a stable kind of jet with a high energy outflow efficiency. But for a larger Bondi radius, and here I say Bondi radius of 500 Rg and larger, but actually we went up to like 5,000 Rg, I think, which is just order of magnitude smaller than what it is realistically in Sagittarius. So all dynamical parameters above certain Bondi radius converge. So the result is actually more generic than it might seem at first glance. So if you look at the magnetic flux at the horizon as a function of time, and the energy outflow efficiency as a function of time. So I want you to look at this line, which is smaller Bondi radius here, and this line, which is larger Bondi radius here. So you'll see that this line is oscillating around outflow efficiency of 100%, so a very powerful jet. But here it's almost always 0, except for certain points when there is some kind of jet with energy outflow efficiency less than 100%. So not similar to usual magnetic statistics scenario that we think about. And the reason actually is that you have the same magnetic flux in the medium, but you don't accrete it somehow. So you see this magnetic flux as a horizon for the purple lines, it's lower than for this line. So
Sorry, I can't read any of it, so you have to really say loudly, and I
So-
also have trouble hearing it. So
this is large Bondi radius case.
the gray,
It's purple, but yeah.
okay.
And these lines are this smaller Bondi radius
Okay.
case. So this sits at the value of 50, which I think is what is happening in magnetic arrested disk. This value is usually 50. But then as you increase Bondi radius, magnetic flux is not able to accrete into the black hole. So it's lower, it is at a lower value. And so as a result, you don't have magnetic flux and you don't have the magnetic flux to recycle into powerful jet. And the reason for that is actually the flux eruption episodes we talked about earlier. So here I show, you can 3D rendering, saying plasma beta magnetic field lines, but now magnetic field lines originating around the black hole and a little bit to the side from the black hole. So the top row shows the smaller Bondi radius case, and the bottom row shows the larger Bondi radius case. And so time goes from left to right. So you can see here there's a colloidal magnetic field, but also if you extend this, there will be some field lines will be pinched onto the black hole, there will be a current sheet, and so eventually this current sheet reconnects, the flow evacuates from the black hole, it destroys the magnetic field lines, but then as it passes, it meets the high pressure of the medium because the Poynter radius is small, it's higher pressure, and eventually the magnetic field lines are distorted, but they are predominantly vertical. But when you have a larger Poynter radius, not only the pressure of the medium is smaller because of the larger Poynter radius, but also the same poloidal magnetic field has larger distance to stretch over. So you have more radial magnetic field lines here close to the black hole. And so when the eruption occurs here, it also has the ability to propagate along the magnetic field lines radially, and also the emits lower pressure of the surrounding medium. So the eruptions can can efficiently drive turbulence in the surrounding medium. And this turbulence tangles the magnetic field, and as a result, black hole is unable to create the same polarity of the magnetic field. And as a result, it can't create the same sign of the magnetic field and recycle this flux into a powerful jet. So another free parameter I talked about is the initial angular momentum. And what we find is actually initial angular momentum is not that important, because if the medium doesn't have initial angular momentum, it will gain it through the feedbacks, which is the feedback by the eruption episodes, and it will eventually lose its angular momentum because the flow is magnetized and there are magnetic torques. So both the initial low and high angular momentum cases go through low and high angular momentum, and so in the states when you don't have initial angular momentum, or when your angular momentum is low, these eruptions drive turbulence. But when you have the rotation of the medium, this eruption-driven turbulence is sheared, and so then the black hole can actually create the magnetic flux of the same polarity. And so, yeah, the powerful jets can appear in the states when there is sufficient angular momentum in the medium, but any medium will go through states of low and high angular momentum. So there are, in any case, there are states, the black hole goes through cycles of jetted and non-jetted states. So this leaves us to the right of this plot. On large scales, Poynter radius and beyond, so find that the kind of best bet model, so the spherical accretion model that is supposed to produce powerful jets as well as it can do, struggles actually to produce powerful jets. So strong jets are not a generic outcome of accretion in highly magnetized states, even when there is an abundance of magnetic flux available in the medium. And observationally, this should predict in the low angular momentum state strong magnetic fields, even in the absence of powerful jets, which may be consistent with Sagittarius A star. So yeah, I'll want to just, this is roughly the end of the talk, I want to outline some of the discussion points or future directions for all of this, parts. So all of these parts are interconnected, of course, because we need to understand emission on microscopic scales to understand what is happening observation-wise on large scales. And for example, we need to understand anisotropy in the accretion flow to understand what type of anisotropy is there on microscopic scales to produce emission. And on microscopic scales, I think there is still a question of what ultimately sets the anisotropy, in which part of the accretion flows. We talked about anisotropy, but in terms of like limiting cases, what is the maximum effect allowed?
Do you actually believe all these computer things? Do you think any of those? I mean, they are obviously very, very complicated, right?
I think I'm
I
trying.
mean, should not they be used with? Yeah, actually, we should. Sorry.
Yeah.
Of course, we knew she
So we
said
should
not
let
to
her
believe.
resolve before answering an existential question.
I think I'm not kind of trying to simulate reality. I'm trying to come up with like, simplest possible problems, such as like simplest flux accumulation problem and understand its nonlinear dynamics in the simplest possible case. So kind of, this is definitely, all of this is a toy problem that should be somehow extrapolated to reality. But yeah. So again, this is not, I talked about anisotropy. Of course, it's not, it can't be like extrapolated one-to-one to reality, because I said all plasma in the accretion disk sits at the near instability threshold. Is this true? Likely not. Like in the case of solar wind, we see plasma sits at the near instability threshold and Firehose instability threshold, which has to do with, for example, plasma contracting or expanding. So in the accretion flow, you can imagine some parts of the flow being contracted, some parts of the flow being expanded. So you have different types of anisotropies in the accretion flow. So we need to understand what ultimately sets this anisotropy on large scales. Also, we don't understand the, in the case of just this synchrotron, anisotropic synchrotron emission, we don't understand the propagation properties of the emission. So again, I talked about the emission intensity. I can talk about intrinsically emitted polarization, but we don't know the propagation of this emission, propagation properties, or the irradiation and conversion coefficients. Here on this scales, obviously, this is a very toy model to just compare what are the differences between fluid and kinetic approach to hope to go to larger scales with the new GPU accelerated code, particle cell code entity that can help to develop. But also just better understanding the collisionless accretion problem. Kind of in the fluid approach, we have 1D accretion, we have torus, stuff like that. But for example, the torus hydrostatic equilibrium, it is actually unstable in collisionless plasma. So it's interesting to come up with some kind of collisionless reference solution that is stable in some regime at least. On large scales, obviously, like I talked about the very maximum model to produce the powerful jets, but in realistic scenario, they won't be colloidal magnetic flux, and they won't be torus as in MAT simulations. So what sets the flux transfer, for example, from the ISM and stellar winds onto the black hole, and also find that there are jetted and non-jetted states regulated by the angular momentum transferred. So what sets the angular momentum transferred? Is it the net transfer from the black hole? Is it the flux eruption episode-driven feedback or jet-driven feedback, something like that? And also you might have seen the flux tubes. This one here, this are actually flares, so the flux eruption episode that are connected, kind of anchored by the magnetic field lines to the jet, and they extend. So, and they just sit there when there's no angular momentum in the medium. So what is their role? They are likely filled with non-thermal particles. So yeah, I'll leave you with my takeaway points.
All right. Well, okay, let's go. So yeah, I think we're out of time, but certainly this is going to be around till at least what 4:35 or so.